Okay, looks like we have started, right? Should see me. Okay, thank you for joining our AI testing talks. My name is Rostislav Yavorsky, and I am head of research at Exactpro Systems. And today we continue my short course on anomaly detection. And I hope you attended my previous lecture, number 1, which was mostly very introductory about numerous examples why anomaly and outlier detection is very important. And today we'll speak about statistical methods. So let me share my screen. Okay, you should be able to see my screen. So lecture number 2, anomaly detection for AI testing, and we'll speak about statistical methods. So let me start from reminding you the most basic terms of our course. So outlier is just a data point that differs significantly from other observations. And again, just let me repeat again and again that this is not formal definition, because significantly is not something you can easily formalize. And the second definition is slightly more wide. So sometimes we're not looking for just one data point, but maybe for some patterns, and we use term anomaly, although these terms are interchangeable. Usually we use term anomaly for patterns in data that do not conform to a well-defined notion of normal behavior. Again, before defining abnormal, you need to know what's normal, and that's not really easy. And we'll speak about it again. So this is the plan for today. We start with very simple graphical methods and very basic notion of interquartile range. And then gradually the technique will be more and more advanced, and we'll finally speak about statistical hypothesis test and p-value and t-statistics, etc. So let's start. Our main goal during this course is to figure out how to detect anomaly, and usually the simplest approach is just to visualize your data. So once you have a picture just in front of you, then you can easily figure out that, okay, this could be probably anomaly and this could be outlier. So the first method is just to build a graph, and the histogram is probably the simplest solution. So for those who are not maybe very good in this, let me remind the definition. So you just divide the entire range of your values into several intervals, which are called bins, sometimes buckets. And then you just count how many values fall into each interval. So here, each bucket is colored in different color. Probably, okay, this probably nice for the lecture, but usually people don't do that this way. But anyway, you can easily see that values around 4 are quite frequent. Then some values are not, and the value you see, so in your data set you have value which is close to 12. It's here, and that looks quite like not really normal. So that could be possibly an anomaly or outlier. So here are a more practical example from real life, and you see that sometimes your graph could be unimodal. So you have just one interval with kind of most data which are here, and then you see here some possible outlier. It's easily see from the picture that it could be somewhere here. This is another example where you clearly see that you have at least 2 different groups of data, which probably is different distribution. So that's not that simple to analyze. But anyway, even from this graph, you see that there are some values which are far from kind of standard. And again, that could be kind of candidates for outliers or anomalies. And this is another example. So anomalies here on the left. Another very useful and very important technique is scatter plot. So what's kind of a big part of histogram? So with histogram, you can only visualize only one parameter. So you have like some height or weight or something else. You just count. So you visualize how this parameter is distributed, but usually your data has much more than one parameter. And scatter plot is a technique which allows you to visualize two parameters. For example, look at this picture on the right. You have some data which describe ice cream sales depending on average day temperature. So you measure some like your weather parameter, like 16 degrees, 22 degrees, I think Celsius, and then you sold so many ice cream. So you have some income generated like $100 or maybe $500, and you definitely see when the weather is cold, then your income is smaller. When the weather is hot, then definitely you sell more ice cream. So again, the technique is quite simple. You use one axis for temperature, another one for sales. Then each particular data item here, it has two parameters like this one. 15.2 is somewhere here, right? Yes. And 332 is somewhere here. So this point corresponds to this data item. So this technique is much more powerful because you can visualize relation between two different parameters. But again, what's a big part of this picture is that the order is not visible here. For example, it might happen that the order is important for you, that this was the first day, second, etc. But here on the picture, the order kind of is lost. So you just have the set of these points. It doesn't matter which order they, it does matter, but you cannot see it on the picture. So in which order they arrived. So here are some examples from real life. And you see, sometimes it's quite easy to figure out that these two points probably are candidates for outliers. Sometimes, yes, it's behaves like this one. So you might have quite many data points. So you can use not points but circles just to see the more dense area, etc. Sometimes you have some kind of pattern, linear, or like here maybe something more complicated. So you see sometimes quite simple to analyze this kind of picture, but more often picture does say something to you. But again, it relies on your intuition, on your experience, whether you can see if, okay, this is definitely look like outlier, and this probably too, but if you speak about these 2 points, it's definitely, I'm not sure, because again, it depends on your domain. Sometimes it could be, sometimes it's not. So, but this is very useful technique. I really recommend it to use it. And right. So what's good about this technique, that you can actually see the data, and sometimes it's very useful, but sometimes it's not. For example, you need to design some automatic tool which will check maybe even simple test of outliers, and automatically produce this list of candidates and send it to you or to manager. Then involving a human is not a good choice here. Then so you need some formula, and probably the simplest formula to detect outlier or anomaly is Interquartile Lynch. And let me speak about this one. So again, still very simple but very powerful definition from statistics, the definition of quartile. So there are 3 quartiles for every data set, and here are kind of more informal definition. So Q2, which is second quartile, is already known to everyone as median. So it's the value separating the higher half from the lower half of the set. Then actually you find median inside the lower half, and it's called the first quartile. So it's the middle number between the minimum and the median of the data set. And similarly, the third quartile is a middle value between the median and the maximum of the data set. So because this is a really important notion, let me maybe spend a couple of minutes more on this definition. So once you got this Q1, it means that 25% of the data, a quarter of your data is exactly 1/4 is just below this number. So Q2 is the value such that 50% of the data lies below this point. So and another 50 is above. And then third quartile is a point such that 75% of the data lies below this point. So first one, second one, and third one. So usually people don't use term second because median is kind of more typical term, but actually median is the same as second quartile. So let's consider the following example. Like you have raw data, like 3, 2, 3, 4, 9, 2, 10. I don't know what it could be, just anything. So you just have some measurements. So in order to compute your quartiles, you first need to order the values. Like you see, the smallest one goes here, 2, then you have another occurrence of 2, then it goes here, then you have 3 from here, another 3 from here. Yes, this is another 3. So it goes here, then you have 4, here's another 4, and 6. So very simple procedure. So the idea of this technique that you can easily implement it manually using any script or programming language. So it's quite simple and doesn't require any advanced mathematics. So once you order the data, then it's immediately you got the quartiles. So here 6 is the median because it lies exactly in the middle. So then you have minimum, it's clearly 2. Then you have maximum, it's clearly 10. And then first quartile is the value just in the middle. So you see 3 below, 3 items is above, and this is the lower half. And the similar way upper half, you have 3 numbers above, 3 numbers below. So here you have Q3 is the third quartile. So what's really also very useful and very important from this technique is this is called 5-number summary. So typically we don't have much time to communicate our insights from data analysis. For example, you got some data, you are an analyst, and you're speaking to some colleague, friend, or manager, and he or she is asking you, okay, tell me just a couple of words about this data. And if you're really short of time, just say maybe one word. Okay, the average value is like 22. Okay, so our sales, for example, annual sales are around like 52 something, and this is kind of 1-number summary. But sometimes you need to add more information and use 3-number summary. You say minimum, maximum, and some average, a median value. You say, okay, like our daily sales or weekly or whatever is 22, but the minimum is like 19. So it's never below 19, and the maximum is like 32. So we do have some value 32 in our data set. The minimum value is never below 19, but average number is 22. So this is already much more information. So it already gives you expression that actually you understand, you have more kind of feeling, intuition about the data set, and the more informative way of short summary is called 5-number summary. So when you provide not only minimum, maximum, and median value, but also the quartiles. So, and this is this notion of quartile is the basic of very well-known Tukey fences test. So John Wilder Tukey is a quite well-known mathematician. I just recommend you to read his biography on Wikipedia. You'll be impressed. So he's really a cool guy. So he suggested to use this, again, quite simple, but why it's useful? Because it's completely automatic. So you don't need to visualize anything. You need to look, you don't need to involve human to look at your pictures, at your scatter plot, at your histogram. So you just implement it, and automatically you'll get a script which, okay, says this is outlier and this is not. So the idea is quite simple. So you use the formula, just take Q1, first quartile, and then you minus some number of interquartile Lynch, where usually K is taken to be 1.5. And again, this is a magic number, but it comes from experience of many people. And similarly, Q3. So Q1 and Q3 here are exactly the lower and upper quartiles, which I just described. And K is some non-negative constant. So you can play with it. Maybe for your application, you can take different value. But usually, if you take K 1.5 and some data point falls outside this interval, then definitely it's outlier. And if you take K equals 3 and some data point falls out of your range, then it's kind of far out outlier. So let's see our example. So here's just the formula I copied here. So in our case, the first quartile is 3, right? It's here. Then the third quartile is 9, right? So the interquartile range is the difference between the third and first quartile is 9 minus 3 is 6. So 6 is some kind of the size of our core of the data. Then we just take Q1 minus 1.5 this size. So it will be 3 minus 1.5. 1.5 is the magic number, 6 is the difference. So it will be 9, 3 minus 9 will be minus 6. And here, I see, you see this typo, that must be Q3 here. So Q3 plus, so yes, it's here 9, Q3 plus 1.5 times 6, so it will be 9 plus 18. So what does it mean? So that if at some step you get data point which is below minus 6, so you see here just lowest point is 2, or something which is above 18, and see so far you have maximum 10, then according to Tukey fences, these numbers will be outliers. So according to this test, you don't have outliers in this data set at all. So which, I mean, even the smallest and the maximum, the largest values are not actually even candidates for outliers. And again, the main advantage of this data set is it's very simple, it's very easy to interpret, and it could be implemented automatically with any specific knowledge of programming or mathematics. So, but again, this fine number summary could be visualized using this kind of diagram, which is called box plot. And the idea is simple, right? So you indicate this interquartile range with it's colored here with kind of pink, and so you can indicate minimum, maximum, and sometimes you draw it like for your data set, and sometimes you just remove outliers, and then you draw this box plot, and then you put the values for the outliers. So this is very useful, very simple, very widely accepted type of visualization in statistics, so box plot. And sometimes it's kind of written this way, like maximum on the top, minimum on the bottom, and this first and third quartile are here, then median is indicated here. Sometimes, and this is exactly our example, sometimes you draw it horizontal way, right? Again, so minimum here is 2, and first quartile is 3, you see, then 4, 6, 8 are just our data points, and 9 is here, it's third quartile, and maximum value is 10. And this is just another example from more real life. And what's here? This is quite funny example. So time slept hours here, and here you have like 7 days of the week. So assume you just had some survey in your office to check how much time
do people sleep, I mean, every particular day. So let's see the Monday. So you have, there is a minimum value. So there is a person in your office who slept just 4 hours, but there is another lucky guy who had like 9. But you see the median value is something like 7.7, and third quartile is around 8. First quartile is something like around 6. So you see the majority of your, like half of your friends, colleagues just live between 6 and 8 hours, but there are some kind of minimum max value. So let's see Tuesday, and you see the average kind of is below, slightly low than Monday. So the medium is just below 7, but you see the minimum is more. So probably this guy had a party during the weekend, but no party on Monday. So at least 5 hours is the minimum. And you see some outlier. There's a lucky guy, probably he or she had some deadline on Monday, so he was kind of lucky, or maybe his vacation starts on Tuesday, so he spent in bed almost 11 hours. Or maybe this is just this guy who had a party on Monday, then you cannot just have 2 parties in sequence. So he decided to just took a day off after just completing urgent task on Monday. So you have here like more than 10 hours. So you have Wednesday, which is again average even smaller than Tuesday, and Thursday is even below, but Friday becomes much better. So you see even the minimum is 6, but first quartile starts above 8. So you see, so you have 5 numbers summary for each of the day. So you put them on just one screen, and you have quite good understanding of what's going on with this parameter. Again, so you have visualization of just one parameter, just one single parameter, time slept in hours. But anyway, this is quite useful and very informative. So that was quite simple part. Okay, let's gradually move to more advanced technique. And now we'll speak about time series. So you have, for example, some measurement which goes over time. Oh, probably that was just a good example of time series. So you have a value you measure daily, or for example, it could be measured hourly or monthly or every second, or doesn't matter. So you have some time series, and you need to figure out some anomaly in this series. And then one still simple but powerful technical is called seasonal and trend decomposition, which the abbreviation is STL. And the idea is for those of you who know what's linear regression and linear approximation, this is kind of generalization of generalized version of linear approximation for more advanced trends, which could be not linear. So the idea that your algorithm decomposes a time series into 3 components. The first one is called trend. It is red on this picture. The second one is called seasonal, and then the remaining part is called noise. So this already uses some advanced mathematical technique which is called loss from locally estimated scatter plot smoothing. And okay, for this technique you probably would not like to implement it yourself. I would suggest just take out of shelf some maybe standard library or whatever. So there are a lot of different implementations on the web. So, but basically the idea that you have some kind of raw data. So you see it's on the picture above, and you assume that, okay, this is your basic assumption of this method, that it could be decomposed into 3 components. First, you compute trend, which could be any kind of of this kind of curve. So for example, you have some sales or like traffic on your web or whatever. So you assume that traffic couldn't be the same like yesterday and today, because for example, it's different season, like you maybe invested something into your marketing campaign, and etc. etc. So you have some trend in your data, and also you might have some seasonal components. For example, if you have some weekly data, always you will have something different during the weekend and during working days. So you have something which is heavily related on the date of the week, for example. And then the remainder part. So let me remind you that our topic is anomaly detection for AI testing. And I assume you already understand the basic idea that in order to define, to find out anomalies, you first need to define what is normal. And in this approach, your assumption that normal is combination of trend and seasonal values. So you see that, okay, we assume that this seasonal graph is kind of normal behavior, and this trend is, okay, it is explainable kind of part of your data. So, and then you just try to find out kind of the best approximation of this two. And then the remaining part, the remainder, is located here. So you don't need to look at points here, but instead you try to analyze remainder in order to find your anomalies and outliers. So you see, like here and here, you see some really deviation from your trend and seasonal behavior. This could be a candidate for anomaly. This is another one, and this is another one, etc. So you see, basically, this is quite useful and powerful method, and there are quite many good texts on the web about this method. I really recommend you this paper on Medium, which is about anomaly detection using STL from monthly airline passengers data. So the link is here, and you can easily find it. And another good example for applying STL is web traffic data. So this kind of data each of you can easily access by installing Google Analytics or just any other statistical analysis for your web page. So this data could be very well analyzed using this method. Okay, still have some time. Let me switch to the final section of our today lecture. It's about statistical hypothesis test. So the idea is that for statistical methods, working with hypotheses and parameters is kind of quite a well-known technique. So this task to check whether some hypothesis is correct or not, it was well studied during the 20th century. So a lot of quite powerful and interesting methods were developed. Let me just give you a short introduction into this topic. So usually to use this method, you need two hypotheses. The one which is called null hypothesis, it assumes that kind of everything is stable. It's stable, like we have normal behavior, so the observed difference is due to chance alone, and there are no anomalies. So definitely we are working with the random variables, so you cannot have the same data today as you had yesterday or the day before yesterday, but all changes you have are just due to chance alone. So, and then you have the second hypothesis, which is called alternative hypothesis, which says that the parameters of the distribution have changed. So actually you have anomaly and the data has different distribution. So once you define these two hypotheses, there are different tools how to measure how this second or first hypothesis is kind of true. So the first very important characteristics of your data is called p-value. So, and it's really important, that's probably the most important notion in this area. It's widely used by statisticians and in different applications. So what's really p-value? So p-value is the probability of obtaining test results
which are at least as extreme as result which you got. So let's look at this picture. So assume you have quite, okay, you almost never have seen application. Okay, let's assume you have a very nice symmetric picture of your distribution, but p-value surely works for any kind of distribution. But at least for this example, let's assume you have this nice curve. So this is a probability of different values. So the total area below this curve is equals to 1 because to 100%. So this is kind of all possible values. So here you have kind of peak of your distribution. So more likely observations are located here. And so you expect some values around here, which are kind of here. And then you perform your measurements and you get this data point. So this is the observed data point. And you realize, okay, it's not really among the most likely, but it's not actually look like anomaly. So it would be really nice to have some tool how to measure your feeling, because again, once you each time you need to do it manually, to do it like with your observation, with your kind of visual, to apply visual presentation, it takes you time. So you would really prefer to have some automatic test. We just compute some value, apply some test, and then it says, okay, this is just anomaly 1, anomaly 2, and this is number 3, just another candidate, which you should consider might be or not. But okay, so p-value is exactly the technique to measure how far is your observed data point from more likely observation. And the idea is that p-value is the area below this curve, which is kind of above this value. So you got this result, for example, like 22 or 25, doesn't matter. And but still, it's possible to have 26, 27, 29, like even maybe 40 is still possible according to your distribution. But the probability of these values is really small. So in order to measure the probability of your alternative hypothesis, you compute the sum of all probabilities which are above your observation. So actually, p-value is just used to quantify the statistical significance of your result. So if p-value is small, so if this area is small, that means that the probability of your kind of that everything goes well is quite low. So it means that your outcome is really unlikely under the null hypothesis. But let me remind you that null hypothesis is that everything goes okay. So if you have very small p-value, then most probably you have anomaly. And if let's consider another example. For example, you computed some observed, you observed some data point, and you had a feeling like, okay, that's probably an anomaly, but then you compute p-value, and it turns out that p-value is something like maybe 50%. Okay, not 50, even 20% is quite big value. So usually it's considered like anomaly if it's less than 5%. So 20% chance that you can observe something even far from more likely observation. Then with p-value 20%, you would say no, definitely it's not like anomaly. That's just another. Okay, that's because of your random nature of your data. So, and another parameter which is quite usually used is called t-statistics, and here is another simple formula. So you have estimated value, you have your hypothesis, and then you just normalize this difference with your standard error. So let's see this picture again. For example, your expected value here is like, okay, let me say 22, and then you observe 25. So here, estimated value is 22, observed value is 25. So you say, you see, our observation differs from our prediction, like the difference is 3. But again, it may sometimes 3 is something small, sometimes 3 is something big. So you need to normalize it with standard error. So the immediate question is, okay, and what's the standard error of your data? And if standard error is like 6, then you say, okay, then 3 divided by 6 is like just 0.5, so difference is not that big. So if your standard error is rather small, so typically you have like observation 22 and standard error is below than 1, then observing 25 is different story. You see, and okay, so that means that 25 in this case will be quite a candidate for anomaly. And this t-statistic is usually used along this p-value. So typically you come to your boss, you manage, say, okay, you see, we have observed value like 25, and it's quite far from our prediction, and the p-value is rather small. So, for example, less than 5%. So the chances that this is just due to our kind of standard random error is very low. So most probably this observation is anomaly, is outlier. So let's analyze it. Why it happened. So this is actually all I have for today. And before conclusion, like I mentioned, some of the techniques could be easily implemented manually, like computing quartiles, interquartile range, or this 5 number summary. But the more go deeper into statistics and dive into different methods, you definitely would prefer to use some library. And here just link to very kind of popular, powerful, and famous library, which is called SciPy, which definitely includes different statistics, but also a lot of algorithms for optimization, integration, algebraic equations, differential equations, and eigenvalue problems. Next lecture, we'll speak about machine learning approach to anomaly detection, and this will be also useful here. So for different methods and many other classes of problems. So definitely for more advanced technique, you don't need to do it manually yourself. You can use different libraries. It's just one of them, and surely there are different options too. So thank you again, and questions are welcome. So most probably we'll have a separate session for questions answered. Just if you're looking the recording, watching the recording, just put them in the comments, and I hope I will have chance to answer you. So we still have one more lecture in this mini course. Like I said, it will be about machine learning approach to anomaly detection. Most probably next week. Just okay, see the announcement. Thank you very much. See you. Okay.